All right. So let's go through these. We've got the first one that says, of the 15 people in the class, 3 are chosen to leave early for lunch. Is it a permutation or a combination? What do we think? Why? Because it doesn't matter if you leave first early for lunch, if you leave third early for lunch, it's the same thing. You're still leaving early for lunch. So I would say that this one is a combination. Because order does not matter. That's the way I would word it. That is the only difference between permutation and combination, is that in permutation, order does matter, and in combination, order does not matter. So then we were asked how many different ways could they be chosen. That's when we're setting it up in our notation and just typing it in the calculator. Like, we don't have to do this by hand. I had a lot of people on the skills check did it with the whole formula. Notation, calculator. Skip the formula step. Because all we're doing is we're taking our 15 people in class, doing a combination, choosing 3. And we type that sucker in the calculator. That counts as showing work. When it says show work, it means that. Give me the notation, type it in the calculator. You do not have to put it in the factorial formula. Save yourself some time. So type this into the calculator and what do you get? 455? 455. All right, question number 2. And just to point out, for number 1, that is a 100% complete, fully work shown answer right there. That is the extent of work that we need to show. That would get 100% on the answers, okay? Do not have to put it through the formula. Use the calculator, use the tools at our disposals. Okay, for number 2, we've got 15 band members who play drums, and there's 74 total people in the band. If we pick somebody out of the band at random, what is the probability of not picking a drummer? So we want to know the probability of not picking a drummer. What do we think? Say it a little bit louder. 59. Yeah. Because there's 59 not drummers out of 74 band members. Which you can either get that from going, okay, 74 minus 15. Or the formula that we wrote was also 1 minus the probability, so 1 minus the 15 over 74. Either way is fine to get you down here. As long as you wound up at this answer, you're probably fine. The way you did it was fine. Except we were told to express our answer as a decimal. So let's do that. 59 out of 74 is what as a decimal? That one, I don't know. I was like, I don't know what I'm supposed to do. Yeah. 0.80 because it's 0.797 and they say round to the nearest hundredth, which means we're looking at 2 decimal places. And that 7 pushed our 79 up into 80. Exactly right. And our last one is another one of these, evaluate the expressions where we substitute stuff in. Substituting things carefully. Make sure we're paying attention for our parentheses. I'm going to do my A of 15, my B of 6, and my C of 0. So I'm going to have my 6 squared minus 4 times 15 times 0. Substituting everything in. Then we're going to come through and simplify. I've got that 6 squared. We do that first. What is 6 squared? 36 minus 4 times 15 times 0. Yes, it's 0. Anything times 0 is 0. So 4 times 15 gives you 60, but 60 times 0 gives you 0. So we wind up with 36 minus 0, which is just 36. That was our answer here, and this was our answer here. Okay. Questions on this one? Okay, so what we're going to work with today is page 16 in your notes packet, and we're getting pretty close to the back of it. In fact, we only have 3 more pages after today. Which we'll get through those tomorrow and Wednesday. That'll leave Thursday for review, and Friday's our chapter test. All right, so we're going to talk about the difference between a theoretical probability, which is for the most part what we've been working with lately, and the experimental probability. So the theoretical probability are those kinds of questions when I grab my die. When I pick up a dice and I say, what is the probability that it lands on a 1? And we say, what? What is the probability that this lands on a 1? 1 out of 6. That is a theoretical probability. We are making a prediction about what's going to happen. So a theoretical probability is, we're going to define this as what is mathematically expected to happen. We expect that 1 out of every 6 rolls of Big Mom is going to land on a 1. That's what should happen. The experimental probability is if I do roll this and start rolling her, and we get a 6, and then we get a 1, and see, I've got my 1. It's what's actually happening when I roll it. So the experimental probability is calculated from your actual experimental data. Calculated from experimental data. So we could use my die here as an example. I just talked it through, and we think our theoretically, we should get 1 out of 6 for my die to land on 1. Well, I just rolled my die twice, and I got 1 on one of them. So my experimental probability, I only ran the dang thing twice. From the experiment I just did, I got 1 out of the 2 rolls that I did. Granted, it wasn't a great experiment. I only did it twice. I only rolled it twice, but I got 1. So it's what we get from our experiment, what we get from our data. So our experimental probability doesn't need to match our theoretical probability. In fact, a lot of times they won't, but they should hopefully be close. Oh, sorry. It's being grumpy. Come on, man. Okay. So what we're going to do is we are actually going to practice this. We are going to, stop freaking out, iPad, thank you. We're going to actually do a little experiment before we talk about the next line in there. I want you and somebody who sits at your table to work together. And what you're going to do is you're going to flip a coin 10 times. Before you do, I want you to think about it. Before we start flipping, so I'm going to pass the coins. Before we begin, if you were to flip this penny, which I do want all my pennies back, these are from like my actual change jar at home. If we were to flip a penny, how many times would we expect it to land on heads? Or how often? 50% of the time. 1 out of 2, right? So if you guys flip these 10 times, how many do you expect it to land on? 5. So, work with the person next to you, just because I don't need it to take forever and I don't have that many pennies. Do it 10 times. Record how many heads you get on your coin. You can put it at the bottom of page 15. You can use the dry erase portions on the desk. I'll get the markers out. Or you can put it at the bottom of page 16. Alright, I'm going to put some dry erases out by where all the stickers are. Yeah.
It's not. We're gonna
Yeah, you're just counting how many heads you get in 10 flips.
And then we'll write for me off.
Do you know how to put this on? Alright.
Me neither.
I've got dry erase.
So,
Yeah, you want to do that? Alright, calculate it for 10 flips.
Well, I mean, I'll try. I'm really bad at it. It's weighted on heads.
You're right, just either at the bottom, like in an open space in your packet, or on the dry erase portion of your desk. It doesn't matter to me. We're going to look at the data all together here in a second.
Okay. And it's heads. Yay! Something different.
All right. So I feel like the coin flipping has kind of slowed down. So we expect our overall results to be about 50%, or about 0.5. Or since we did this 10 times, we should expect maybe 5 out of 10-ish. That is what our theoretical probability would be. What did you guys actually get for your data? How many heads did you get in your data?
I got 2.
2. So we got a 2 out of 10. 7 out of 10. 6 out of 10. What else we get? How many? 3 out of 10. Everybody get some variation of here, but anybody get right on 5? Statistically, it is likely, but it's not guaranteed to
We
happen.
got 7.
7. Yeah. And that's okay. When we do experiments, our data might be slightly different. Nobody got exactly right, but if we kind of spread out our data, it looks vaguely kind of centered around it. And in fact, if we did this experiment over and over and over and over again, it would get close to that data. So what I have here is an experiment that's going to do it over and over and over and over and over again. So it's going to do, instead of 10 coin flips, it's doing 25. And it's going to do that same experiment of flipping 25 times, 20 times in a row right here. It's going to start. And it's going to put the amount of heads on the little chart right there. that it gets from doing this experiment. So it's repeating it over and over and over again. And it did it 20 times, and I can run it again. And it's running again. So the more times we repeat this experiment, the more data we're getting and the closer it's getting together. And we can kind of see what shape it is the more often we do the experiments, that center, where that kind of blue line is right there it's right now at 49.3% heads, which is really close to our experimental of what we thought was going to be 50%. So we should wind up somewhere around 50%, and the more times we do this experiment, yeah, we occasionally get 80% heads over here. Occasionally get a group with 20% heads, but it's not super common. The more times we do the experiment, or the more flips we do per experiment, the closer and closer and closer it's going to be to that mathematical, theoretical probability. And that's what we're talking about today. We're talking about that if we do it more and more times, it's going to get closer and closer to what we think it should be. And in fact, if we look, I don't know if it'll let me zoom in up here. No. If we look really close on this graph, let's see if I can make it bigger. That did not help. It just stayed the same. Okay. It's talking about a width here as well, and what that's giving us is a margin of error. So it's saying our mean here, our average is 49% with that margin of error of 1%. So it's saying more than likely our experimental center, our true center, is between that 48 and 50, which is what we expect it to be, assuming all of our pennies are fair. Pulled them out of the coin jar this morning. It should be. Unless somebody gave me a trick penny somewhere. So that's what this is. So what we're going to talk about is the law of large numbers, which we actually just used a whole bunch. The law of large numbers says when an experiment or an event is performed a large number of times, our average result is going to get closer and closer and closer to the true average, which should be our theoretical probability. That's what the law of large numbers. This is the actual definition. I just don't have it set up as a I read it part. So this is what you want to put next to law of large numbers on page 16. And we're going to practice this again because it's a little weird. But we're not going to practice it with the coins again. We're going to look at someone else's experimental data. But I'm going to show you the shape. So I want my pennies back. We're going to be done with the pennies. There you go. I did. Yeah, I want a penny back. To be fair, they want pennies. That's what this is right here. Okay, it's when your experiment is performed a large number of times, the average result is going to get closer and closer to the true average. That's the law of large numbers.
Penny. No, that's our penny. He took my penny. I don't have your penny. He dropped his penny. You took mine. No, it's right there.
Yes.
That's our penny. See? That's our penny. No, right. I don't. He doesn't want that penny. I don't have your penny. I don't have your penny. We gotta do this.
He's stealing my pennies, y'all.
We gonna find it soon.
Yeah, we gonna find it. Because you know the public school teachers is definitely not known for their money, extra money. Which is also part of the reason I chose pennies, not quarters, and his quarters disappeared. Why do you think I dug through and found pennies this morning? All right, so this is our definition for the law of large numbers, and we're going to practice this again. So we're going to look at an experiment here. And this is talking about an 8-sided die, so it's not the run you think about. It's an 8-sided die. It looks like this. It looks like 2 pyramids stacked on top of each other. So this is what an 8-sided die looks like. Kind of looks like 2 pyramids. But it has 8 sides, which is what we need to know. But sometimes it helps us to see the visual. Like this. Yes, I have several of them. All right, so they did this experiment. This is on your page 2. We want to find both the theoretical probability and their experimental probability. So, theoretical probability means if I look at this, what is the probability it lands on an 8? It has 8 sides, and each one of them has a different number on them. 1 out of 8. It is what we normally think of when I ask you a question about a die. So our theoretical probability, it should wind up as 1 out of 8. Which if we get that as a decimal, it would be 0.125. That's what 1/8 is as a decimal. Which means theoretically, each of these numbers should have about a 12.5% chance of being landed upon. Like, that's what it should be theoretically, assuming all of my dice are fair. So then we have the data here from someone who did this. They took one of these dice and they sat here and they rolled it and got a 1, and they rolled it and they got an 8, and they put it all in that table, and they did it 200 times. So they sat there and recorded them all, which is why we're not doing it. That's a long time. And it gets very boring and very repetitive unless you're paid for it to do it as like a scientist. So our experimental data, our experimental probability, we're going to use the actual data that they got. And this is a frequency table. We've seen these before. How many 8s did they roll? 42. Out of how many dice rolls? 200. So our experimental probability is those 42 8s that it rolled out of the 200 rolls. So it's using the data from the experiment. What is that as a decimal? .21, which means what is it as a percent? 21%. If it was over 100, you'd have been exactly right, but since it's over 200, it's a little bit different. Okay. So that 8 was coming up a lot more frequently. That was a really lucky die. If we expected, so now we're going to make a guess, a prediction using our theoretical probability. Doesn't use our experimental probability. Whenever we do our predictions for what's going to happen, we use our theoretical probability. Because the more times we do it, just like if I kept hitting start on our experiment that flipped the coin a bunch of times, if I kept doing it, it kept getting closer and closer and closer to the middle, the real one. So if we did this experiment, but instead of doing 1,000 rolls, she did, or instead of doing 200 rolls, she did 1,000. How many times would we expect them to roll an 8? Yeah, it's kind of weird, huh? So what if it was, well, let's go back to coin flips instead of thinking about these weirdo dice. If I did 100 coin flips, just kept going, 100 coin flips, about how many would you expect to be heads? 50, right? Making that prediction, half of them should be heads. So how'd you figure out it was 50? We took that 100 times 0.5, right? So we take our total number times our theoretical probability. So if we were to roll a 8-sided die 1,000 times, how many probably will be 8s? We take our 1,000 times our theoretical probability. we take, yeah, our 1,000 times that theoretical probability, that 0.125. So there should be, as we do this more and more times, if we get up to 1,000, we should get 125 eighths. The more times we do the experiment, the closer our results should be towards that theoretical probability. The more and more times we do the experiment, the closer and closer it should be to our theoretical probability. Say, is it not Carter, and then don't hide from the window. I did not see you. Thank you. Okay, so it's a little weird and a little awkward to do. So we're going to think about this again. This one's not in your table, but I want us to think of it again. So now they're going to talk about they're thinking about one of these guys, regular ones. We try and make the ones that you guys do without me significantly more familiar shapes. So now look at the weirdo dice anymore, this regular one. So somebody tosses this die 150 times and they get this table. I want you to give me the theoretical probability of rolling a 5 and then their experimental probability of rolling a 5. And then we're going to do a law of large numbers expansion of law of large numbers. We're going to do 10,000 for our prediction. Okay, so we're going to do our theoretical probability, experimental probability, and a law of large numbers of 10,000 dice rolls. Because we don't want to have to do that to figure out how many we should get. That is a beast of an experiment. I want you guys to try this. All right. So what is the theoretical probability of rolling a 5? So theoretical is our what's going to happen when I hold up the die. I say my probability of getting a 5 is 1 out of the 6 sides. You can absolutely scale that up, but you don't need to. 1 out of the 6 sides. What do we actually get from the experimental data? Our experimental, yep, it's the 24 out of how many flips? 150. So while those are both really handy to do as fractions, it's how we build them, they're not super easy to compare. I can't really tell if we got it close, if we got it right, if our experiment was good. It's easier to compare these if we have them as decimals or as percents. So our theoretical probability was about 0.17. We'll just do it to the nearest percent. So 17%. And our experimental data, what we got was straight on 0.16 or 16%. So we got pretty close. We got pretty close. So if we were going to guess how many 5s we would get in 10,000 dice rolls, I always feel like that's we had an idea. Light bulb. We're going to take our 10,000, whatever our big number is we're trying to predict. We're going to take it times our theoretical probability. Times that 1/6. You can do the decimal, but we can also do the fractions. So if we do 10,000 times 1/6, about how many 5s should we expect if we roll the dice 10,000 times? 1,700. So if you do it with the decimal, you're going to get 1,700. If you do it with the fraction, you're going to get about 1,667. Both of those I would count as right. Absolutely fine, because you can either do it with the decimal or with the fraction. I would count both of those. Okay, so somewhere between there probably would be about what we could expect to be. Let's see. So it's all about taking the data to get our experimental, and the theoretical is what we use to make our predictions. Okay, so I know we've had a lot of days where I talked all the way to the end. So luckily, that's not today. Because that's the end. What? Oh my gosh. So homework 5 is technically due today. So if you got questions on it, now's a great time to ask those. I'm going to pass out homework 6, which, huzzah, huzzah, is the last homework of the chapter. What's up, my friend? Bella from last week? Yeah, we did not do that. Turn that in. So here's homework 6, the last one of the chapter. I will have chapter reviews for you guys on paper probably tomorrow. I'll have them available just so that we have them and can start working on them whenever. Homework 6, you guys can actually do everything on. I'm still going to not have it due until Wednesday, but you guys can do everything on it. Everything else we're doing in this chapter tomorrow and Thursday. Or tomorrow and Wednesday will show up on the review, but it won't show up on this homework, so you didn't want to give it like that quick of a turnover. Oh yeah, 100%. Supposed to give me a pad. 100%. I totally forgot. 100%. So if I do that, please remind me, because 100%. 100% I forgot.